If your last name is A through I, please come on time, line up at 6:15. If you're J through Q, please stay far away from the entrance. It's a narrow entrance. There's lots of you. Please stay far away until 6:25, then start making your way to the door, okay? So like, even if you could be just up on the main level, not even in the basement, stay up on the main level. Same with R through Z, then you're gonna wait till 6:35, okay? I think till 9 o'clock should be plenty of time, but we can stay a little bit later if there's some of you still need a little bit more time. But 9 should be plenty of time, okay? I sent an email out yesterday to those who have a conflict on Wednesday nights. You should have gotten that from me. If you didn't get that from me, I'm expecting you tonight, okay? Questions about the exam? Bring your Sun card. Again, PSA 21, same location and procedure as last time. And then I posted a vocabulary list. This will be most helpful for those of you whose English is your second language. You can look up all those words, find those definitions before the test. Then you don't have to do it during the test. If you want to bring a translating device, you can have a translating device during the test. For those of you, English is your second language, okay? That's okay. But you can look at that vocabulary list ahead of time. Any other questions about the exam? Okay, so today, there's nothing more to discuss.
Office hours.
Oh, right, office hours.
Sorry, recitation.
Yeah, so recitation this Friday and next Wednesday is canceled. So no, because we have fall break. No, Monday is definitely canceled. Don't come Monday. So this Friday, next Wednesday, no recitation. We'll pick up recitation a week from Friday. Okay. So, today's stuff is on the exam. So this is a big study session, right? This is a study session for the last part of the material. So let's get started. Here we go. So we introduced this. It's our exact accumulation function last time. And this is an integral function. Okay? An integral function. And we said that we're going to think of this. Okay, ready to go. Okay, so we're going to think of this as this thing that we worked so hard to get in one expression. We got the piecewise linear function for approximate accumulation. So we're going to think of that integral expression just like this one. It's just like this one. What's the only difference? Extremely small delta x. So in other words, with delta x equals dx. Okay? So watch it. Here we go. Wham! Wham! Bam! Okay? So now they're the exact same thing. Now these two expressions are exactly the same. But when we get super, super small intervals, what about that last partial interval? It just kind of it's just like all the rest. It's just like all the rest. So it just gets absorbed into that first expression, okay? When you have super, super small intervals. So now these two things mean exactly the same thing. Okay, so now you're going to practice. Okay? So I've got a list. What? What's up? Watch the video. You guys think. Don't just copy. Watch the video to get notes, okay? So here we go. So how are these expressions the same? So you're going to take a couple minutes with the person next to you and talk through these 8 items. And the first 6 are about how are these exactly the same, but just using different notations. So go talk through these items. So find each item expressed in both.
You could, but then you would get this thing it's too small. So you just have it taken off.
Okay. You know how fast something is changing. Where is that seen in these two expressions? The rate function. Okay, so you have a rate function in the first one, r of t, and it's the same rate function that we're using. It's just a bigger expression for the input. But this whole thing, right here, all that is the rate function with a slightly complicated input value. Okay, it's the same as r of t. Okay. And we want to know how much of it we have. Where do you see that? Output. That's the output. That's the output of our function, f or a. How much of it we have. Okay? Which is found by summing up. Where do we see summing up? Okay, so in the first one, the German s. The German s. That's the integral sign. It means sum up a bunch of things. Same with sigma. We know that means sum up a bunch of things as j goes from 1 to whatever. Okay? Many bits of change, which we used to say are delta y's, but now that they're so small, they're dy y's. Okay? So where do we see the bits of change that we're summing up? Where are the bits of change that we're summing up? Yeah. Right. And what'd you say?
So the rate times delta x.
Right. Those are the bits of change. K delta x. Okay? K delta x, which we express k now through our rate function. Right? So k delta x, k delta x. Those are our bits of change that we're summing up. Okay? Starting value of x. That should be easy, right? That's a, also seen here. So it's twice in that lower expression. So there's a also. And then to the current value of x. X. Okay? Right, questions on. So you see how these notations are exactly parallel. When you have that ax function with a very small delta x, it's the same function. These are the same. It's just that this the integral notation is a lot cleaner and easier to read. Okay, but it means so. It was important that we spent a lot of time building that ax function so we know what the meaning of the fx function is. So we know what's going on there. Okay? What's the input of each function? X, and what does it mean? So in terms of accumulation, what does x have to do with this amount that we're accumulating? We accumulate up to that point. It's the terminating value of x where we stop accumulating. And so if we let x increase, we get a function. So you let x increase and you get all these accumulations for all these terminal values of x. Okay? And what about the output? So then the output is the total accumulation from a to x found by summing up the bits of change. In this case, very small bits. So the output then is our accumulation, starting at a, terminating at x, for a quantity whose rate is r. All right, questions on this slide? So that's a review of. So now we're going to start practicing with this notation now. So if you get out, I told you to print out or have ready, page 11. Oh. Okay, so number 1 says on page 11, turn to page 11, which was starts to practice your understanding. Define a function f that outputs the exact amount of accumulation of a quantity with this rate of change function starting from x equals -3 as a function of the ending value. Okay, so is this consistent? Is all this stuff consistent with what we just talked about for the integral? There's no curveballs here at all, right? There's no curveballs. So f of x equals, so we want an exact accumulation, that's integral, starting from -3 to, right, so this is a function of where we stop accumulating. That's x. And then, in general, what are we taking the integral of as a whole? What are we taking the integral of as a whole? The rate? Are we summing up rates? Not summing up rates. What are we summing up? Small changes in y, bits of accumulation, which is not rate, but rate times the change in input. And remember, we need t, not x. If you put x in there, then you'll just have the rate at the end for the entire interval from -3 to x. So we need another value of another variable for x that takes on all the values of x between -3 and x. So now we can, but now we know what that f of t is, right? What is it? Cosine of x squared, t squared. Okay? Yes, ma'am.
I noticed from the homework that we were never given well, sometimes we were, but we were given approximate numbers for DT, or we just going to try to do the smallest thing that we can.
Yeah, dt always means like the distance between two atoms.
Okay.
It always means the smallest thing you can imagine.
So is there some number specifically?
No, it's just small enough. It's just small enough so that what we get is indistinguishable from the exact accumulation.
Okay.
So it's just like sufficiently small. So like, yeah, distance between, yeah, but there is no set number that where you cross over from approximate to exact. But we just small enough, just think super small, so that the actual accumulation is indistinguishable from the approximate that you would get. Does that make sense? Good question. Okay, questions on number 1. All right, so number 2, it says we want x to change from 2 to 9. So is this a function or a value? Value, but we can think of it as coming from a function. Let's make a function g of x, and then define this as a particular output of that function, right? So g of x would equal integral from 2 to, I'm going to define it as a function first. 2 to x of, let's use something different now. Let's use u, how about? So there's nothing magic about t, just has to be different than x. So u cubed minus square root of u, need parentheses now with the minus, du. So this is a g function that will solve this problem that's asking about. This function g will be able to solve this problem by doing what? G of 9. G of 9 will be the answer to this because it will be the accumulation from 2 to 9 of u cubed minus radical u du. So do you see what I did? So we didn't need to do that function, but I'm just going to show you the kind of the difference between actually getting an amount of accumulation and an accumulation function. So if we're accumulating from 2 to 9, that's the same as the accumulation function with an input of 9. So what this question is really asking for is just this, what I put the box around. But I want us to really be sure that we see that that's coming from, or could be thought to be coming from, a function whose input is the ending value or 9 of accumulation. All right, so this is what's called these expressions are what are called represented in what's called open form. Why? Because we can't just plug in a u and get the answer like that. So most of the functions you've been used to in your math career have been represented in what's called closed form, which means you have just this expression, you just plug values in and it spits values out, right? You can plug in inputs, it spits out outputs. So this is different than that. It doesn't do that. So in order to get this value, at this point, we need technology. At the end of the course, we'll talk about now getting how we get an actual value for that, or get this g function in closed form, okay? And then we can have this plugging in inputs, spitting out outputs. But for now, we have what's called open form. Yes, sir?
So on the test, the g of x on the left is seen as a function and not a number.
Okay, so he's asking, is this a function or a number over here?
Function, but is it also a number? The one on the right is a number.
Yeah.
But is that also a function? Like,
Is that a number, or is it, so a function means a whole set of numbers. That's what a function means.
so is that the one on the left is just a function? And the right is just a number?
But a function is a whole set of numbers. That's a function is many, many numbers, right? How do we get those many, many numbers from a function? Yeah, you plug in inputs, right? For every input, you get an output. So this is one particular output of that function. Yeah. No, it's all multiplication, right? Doesn't matter. It's all multiplication.
But if you did it,
Yeah. So did I answer that previous question? So it's just about understanding what a function is. A function is a whole set of numbers, a whole set of outputs for different inputs. This is one particular output for one particular input. Was there another question over here? Okay, so if we want to get that value, we need GC or some kind of technology. So at this point, to solve an integral or an accumulation value exactly, so we do Control-Shift-I, and that comes up. And so what do we want? Just we want 2 to 9 of, we used u, so I'll use u cubed minus square root of u, but then we need du, and there it is, 1620.14. What does that number mean? Can you explain what that number we just found? What is that? Accumulation. As your independent variable changes from 2 to 9, when
At a rate of
when the rate function is u cubed minus square root of u. Right.
is it an accumulation of change or just
Accumulation of bits of a quantity whose rate is u cubed minus radical u. Whoa. Okay, questions on number 2. So to get an actual value for these open form expressions, we're dependent on that technology to do that for us at this point. Okay? So why don't you just do these on your own. Just take a couple minutes and do A, B, and A, whatever numbers those are. Just what's on the screen, talk through those for a couple minutes.
constant function. So they rate of change. I said they rate of change of that, or they rate of change of function.
Okay. All right. Let's skip right to the last one. So this one, how could anyone want to explain? What does that integral expression represent? What does that integral expression represent?
It's saying that from -6 to 20, we have a constant rate of 4.7.
Okay. So you're saying from -6 to 20, we have a constant rate of change of 4.7. Okay, that's all true, but what does that mean? So what does that expression mean? Yeah. It's linear. Trevor.
It's saying your delta X is 0.6 because it goes from 6 to 9.
No.
It's the sum of bits of change between -6 and 20.
Okay.
Where every bit is the same. Every bit has the same rate.
Okay.
So it's constant.
Which gives you what?
14 times 4.7.
Does not give you a function. What does the number mean? It doesn't give an exact rate. This is an amount of accumulation. First and foremost, this thing gives you an amount of accumulation. So lots of what you said was true. It's that amount of accumulation that you get when you add up the bits from -6 to 20 at a constant rate of 4.7. So what does a constant rate of 4.7 mean? So it's 4.7 means what? If there's a constant rate of change of y with respect to x of 4.7, can anyone articulate that? Okay. Okay, that's true.
So for every delta x, the output is going to be 4.7 times that.
Almost. For every delta x, for any change in x, what is 4.7 times it? The change in y. So this means for any change in x that you have, your corresponding change in y will be 4.7 times as much as that change in x. So what total change in x do we have? 26. So in this case, we have a big change in x here of 26. So what is the change in y, or the accumulation? 4.7 times that. Whatever that is. So because we have a constant rate of change, we know exactly what constant rate means. It means that for any change in x, your change in y is 4.7 times as much as that. We know our change in x is from -6 to 20, or 26. And so our change in y would be 122.2. Questions on this page? Okay, tub problem. Next page. Quietly, I'll read as you turn. A tub has a clogged drain. It still lets some water through. At t equals 0 minutes, the faucet is turned on. Okay, there's like 5 top hat questions, so we got enough time. So Every time I have to do that, you're taking away your time. So the tub has a clogged drain, still lets some water through. At t equals 0 minutes, the faucet is turned on. The following graph shows the rate of change of volume of water in the tub in gallons per minute as a function of the time in minutes. Okay, so is this a rate graph or accumulation graph? Give you the rate of change graph. So you think of this on the left or on the right? It's like one of the left, when you have the two graphs side by side, it's like a left graph. Okay, so there's some kind of general idea questions here. This is our rate of change. Gallons per minute is up here. Gallons per minute. And this is minutes. So this is some important questions about interpreting what this rate of change function means and what it means for the amount in the tub. So go, work on these. See if you agree. That's what you said. Is that what you said for A and B?
So as long as it's so as long as it doesn't reach that. Yeah.
Are we good on A through C? Any questions? Does that make sense? This is a rate graph, right? So rate. So when the rate is positive, what's happening to the accumulation? Amount of water is going up. So what's happening? The drain is kind of slowly getting better, right? So then after 4.2 seconds, the rate is negative. So the amount of water in the tub goes down. So if we kind of looked at, in order to compare them, you kind of think about it like maybe an average, right? So maybe the average rate here is something like this for about 4 minutes, right? So this average rate at 4 minutes versus this average rate at 3 minutes, which is going to have a greater effect? The amount we added in the first 4 minutes at that rate, or the amount we took out in the last 3 minutes at that kind of average rate? What we put in is going to be more. So there would definitely be more at the beginning than we had at the end. Okay, so what about this volume function? So V of, we can use T, that's fine. V of T equals, we've got rate of change. We want accumulation of water. What are we going to use? Accumulation function is integral from 0 to T of our rate T squared. Something else. So we'll just go with A this time. Doesn't matter. Something else. Then I have to use dA. Little changes in A. Okay, so that would be the exact volume of the tub. T minutes since it was turned on. It's a function of the amount of time that's gone by since you turned on the faucet. Any questions? Okay, so now what if you already had 14? If there was already 14 gallons in the tub and we wanted to get, so maybe that was V1 that I wrote. Okay, so what I wrote before. So now a different version where we started with 14. It's going to be 14 plus that accumulated amount. We started with 14, then we're going to always be adding to the 14. So this will, for any minutes gone by, we'll add the right amount to the original 14 that we had. Okay, what about the change in volume from 1 to 3 minutes? So how can we express that with integral notation, the change in the amount of water from 1 to 3 minutes? So the integral from what to what? 1 to 3. So even though our function starts at 0, we can still write an integral where we start accumulating at 1. So the integral is fine. It's apart from this function b, and it starts accumulating at 1 at that rate. Yeah. Now, what about if I wanted to use function notation to express the same change in volume? How could I express the same change in volume with function notation? So I want to know how the change in volume of the water. How do we calculate a change? Final minus initial. We can just use final minus initial. What's the final volume of water in the tub? V1 of 3. And what's the initial volume? V1 of 1. Final minus initial. So the output of volume at 3 minutes minus the output of volume at 1 minute will give us that change in volume, which will mean exactly the same thing as this. What if I wanted to use V2? Would I add 14? Would it be 14 plus V2 3 minus V2 1? Yeah, so V2 is how much total volume, and it includes the 14. But if we just want the change in volume from 1 to 3, it's irregardless of that original 14. It's irregardless of whatever amount we start with. The change in volume at this rate only depends on the rate. It doesn't depend on how much you started with, right? So I could put 100 here, and this change from 1 to 3 would be the same. So if this was my function, if I did start with 14, I want the change from 1 to 3, I can use the V2 function. It doesn't make sense to add the 14. Lots of students want to do that, okay? But it's the change from 1 to 3. It doesn't matter how much the tub started with. Doesn't make sense. Top hat, let's go.